Hi, everyone. I'm Salma Quraishi. Welcome to Neuroscientists Talk Shop, the University of Texas at San Antonio's neuroscience research podcast. It's November 19th, 2020, and today we're talking with Tad Blair, who is professor of behavioral neuroscience in the psychology department and a member of the Brain Research Institute at UCLA. Hi, Tad.
Hello.
Tad is a neurophysiologist modeler whose work centers on information coding at the level of networks and neurons and how learning alters neural representations to form memories and modify behavior. His lab combines computation, neural recordings, and large-scale population imaging in awake behaving rats during associative and spatial learning tasks. So today in the Zoom, we're joined by former collaborator and fellow navigation specialist, Francesco Savelli. Hi, Francesco.
Hi.
And of course, our regulars, Charlie Wilson. Hi, Charlie.
Hi.
And Todd Troyer. Hi, Todd.
Hello.
So, Tad, there's a recurring theme in your bibliography that connects the search for neural representations with plasticity in the face of behavior, going way back. I guess I went back as far as 93. And that all of this is sort of whether it's identifying key nodes and computations in a head direction circuit or resolving how hippocampal place cells provide a recalibration signal for path integration, or how these same cells remap their place fields during field conditioning. So you've done this really fearlessly at many spatial scales, from synaptic, even like gap junctions, to networks, and more importantly, also across time scales, from sub-second to behavioral time scales that span like acquisition and extinction of memory. So I'm kind of hoping you can say something about how you work with the tension that's famously inherent in this process, where we first have to define like the anchoring first principles that set up circuits and representations in the brain, but then only to a point where we have to leave all that behind and impart all the layers of flexibility that behavior requires. So take it away.
Yeah, so I mean, I'm not sure that I have a grand strategy or plan or scheme for that. I think, like a lot of scientists, I tend to just follow my curiosity where it leads me, and then just try to be as accurate and truthful as possible when I get there about what's going on. But yeah, the question of how brain states encode information and give rise to our sensations and emotions and thoughts and consciousness. This is really, I think, like probably a lot of neuroscientists, it's the question that, made me want to be a neuroscientist to begin with, because in many ways is the question is, what is our conscious experience made of, and so that's a big, intractable, really more philosophical than scientific question in some ways. But as a scientist, what you try to do is, look for models that make these big, intractable questions tractable enough to, get a few answers and make a little progress towards that deeper understanding that you're looking for. And so, yeah, for me, these systems that you study, that you talked about, that I've been studying, the head direction circuit, the place cells in the hippocampus, and so on, I think I have gravitated towards those systems and towards the questions that I've gravitated towards, because they offer what seems like the most promising balance between questions that are hard enough to be interesting and simple enough to be tractable. So that's kind of maybe one of the main guiding principles in my work, is to try to, make progress by striking that balance properly.
It's super interesting too, how you sort of resolve everything to the convergence of signals, right? Whether it's, are we to think of like fear, for example, as really just one input that comes in from, sorry. Or then, in terms of spatial stuff and navigation, it's really more specific, measurable, time-locked, anchored things like body position and, vestibular inputs and things like that. So, but fear, taking a complex behavior, and I noticed in your work, it's not simply the fear conditioning, it's also aversive experience, and the way you're pulling this out in time scales in terms of learning versus extinction and appetitive versus aversive, and how those processes may differ based on what's impinging on the cells that you're looking at is really interesting. And it's
yeah, and the words that we use, like a fear and aversive, and when we do experiments and when we talk about hypotheses that we're testing, we use those words, and I think that it's always necessary to have a healthy skepticism and constant questioning about whether or not you really have a formal definition of those words in mind and around which you're designing your experiment. Because the word fear, for example, is just very open-ended, and can mean many different things in different contexts. And so the experiment that I talked about in my talk today is really an avoidance experiment where animals can avoid a location where if they go there they will be shocked. But a lot of fear conditioning experiments involve being in a confined space where the aversive stimulation is not really escapable. And those are very different, so whether or not what we mean when we say fear in fear conditioning really even applies to the other situation is hard to be certain of. So you almost have to sort of try to design your experiments, focus on the empirical variables that you're measuring, and then, be very careful about bringing in those kinds of interpretive words into the discussion as you look at your results, so, but fear is an example of a motivation, and motivation in many ways is sort of the energy that drives behavior. And so if you're going to study behavior, you can't get away from oh, sorry.
Your turn next, Francesco. With the
life on Zoom is full of interruptions like this. Yeah, but yeah. So I think whenever I use words like fear or reward or any of these sort of motivationally defined terms, I think that what we're often we have to sort of keep in mind that the big picture when we talk about those things is we're talking about the values that are being used to drive decision making, and the way that works may differ a lot in one experiment to the next. So we have to be careful about, I guess, the operational definition of those terms may be quite different even in two similar seeming experiments.
So one thing that struck me in the way you were describing things was that you talked about representation in brain states.
Yeah,
that's related to those, because it's related to general kinds of things like fear or a why or a behavioral state motivation kind of thing. And some of the things that particularly in hippocampal things or head direction system, you have a representation to get a handle on, right? It's not just to study, aversion. You're not studying the dopamine reward signal. You're studying about changes of representations along with these other kinds of states and how they affect each other. And it's particularly interesting in the hippocampal or medial temporal lobe, where they kind of, a lot of the idea is that the representations are kind of self-constructed, as opposed to some sensory coding thing where you're just really focusing on representation.
Mm-hmm.
So I don't know, does that affect how you, or maybe what's particularly interesting to you about the interface between some state and representation?
Well, yeah. So, I kind of have a mantra that I repeat nowadays, like almost at the beginning of every paper I write and at the beginning of every lecture I give in class, which is that, when it comes to neural coding, I like to think about what a neural code is it's a system for mapping states of the world onto states of the brain. So you mentioned, brain states, are really the stuff that our perceptions are made of. Brain states are the stuff that our motivations are made of. Brain states are the stuff that our memories are made of. And so the question is, like, really, what are the dimensions of those brain states that carry information about all those things, And we work now, I think, within a very, I think there's a paradigm that has come to dominate our thinking about brain states in neuroscience, which I think can appropriately be called the population vector coding paradigm, which is that the brain states that matter, the dimensions of the state space that encode information in the brain are activity levels of individual nerve cells, and you take a vector of those activity levels and you have a state that encodes information. And, the stuff that I talked about today very much, lies within that paradigm. And I think that even, in sensory coding, like you mentioned, as well as in hippocampal coding, even though the kinds of things that we're looking at, the kinds of world states, let's say, that we are seeking to find in the brain states may differ when we are studying a sensory system versus a memory system. The paradigm of using neural population vectors as our code words for the brain states, the paradigm of using neural activity levels as the dimensions of the coding space kind of permeates across all of those levels. And something that I've kind of gotten very interested in recently is trying to sort of break out of that paradigm a little bit, like thinking about brain states or coding spaces in which the dimensions are something other than neural activity levels, if that makes sense. And so there's a paper that we wrote recently that that kind of addresses this, and essentially the idea, I don't know how easy it is to get into this, or if it's even a response to your question, but the basic idea is that in signal processing theory, we can represent signals in different representational spaces. And a very classical example of that is like the time versus the frequency domain for representing the same signal. We can map a signal that's represented in the time domain into a completely different representational space by representing it in the frequency domain. All the information is the same, it's just a different representation. And I've come to sort of feel that this population vector coding that we all sort of take for granted and swim in every day, this population vector coding idea is actually just one of two major domains, much like that are analogous to the time and frequency domain, in which the brain represents information. And I'm actually quite interested in looking at that question, not just in hippocampal memory systems, but also in sensory systems and in motor systems, to see, if this paradigm that we have sort of adopted for thinking about neural coding, the population vector code paradigm, let's call it, which permeates so much of neuroscience, if that can be broken out of, and if it can it be broken out of not just in my own personal interesting area of, say, hippocampal memory states, but also in these other in sensory coding and motor coding, et cetera. And I could go on at a bit more length about that concept, but I should probably pause there for comments and feedback.
I think you should say more.
Okay. So let me see if I can explain this without any visual aids. Okay. So the idea that a population vector is essentially the way, the main way can be conceptualized as a vector of firing rates. Okay, you have a neural population, hence the name population vector, It has n neurons in it, and if you give me a list, if you tell me, a list of n firing rates, if you tell me every neuron's firing rate, then I will give you back, I will decode that vector and tell you something, I'll decode that brain state and tell you something about the world or what the brain is thinking. So the dimensions of the coding space are firing rates. They're on neural activity levels, which is synonymous in many cases with firing rate. So what is a firing rate? A firing rate is a time interval. Well, it's the inverse of the average time interval between pairs of spikes fired by a neuron, right? So by definition, a neuron's firing rate is inversely proportional to the average interval between spikes fired by that neuron, right? So pairs of spikes that are fired by a single neuron, the average interval between such pairs of spikes is a firing rate, and is therefore also the dimension of the coding space that we assume to be the main dimensions of the neural coding space when we think about population vector. But what if instead of measuring the time interval between pairs of spikes that are fired by the same neuron, what if we instead measure the time interval between pairs of spikes that are fired by two different neurons, okay? So now instead of measuring the interval between spike 1 and spike 2, both fired by neuron A, I measure the interval between spike 1 and spike 2, where one spike is fired by A and the other by B. That is I can take an average of that interval as well, and I can define that as a coding dimension. And when I do that, it bears a relationship to the standard firing rate that is extremely similar, that is mathematically similar to the relationship between a time domain variable and a frequency domain variable. In other words, there is a conjugate relationship between intervals between pairs of spikes fired by the same neuron and intervals between spikes fired by different neurons. And when you encode something like position in firing rates, like place cells do, or like head direction cells do, you actually automatically, without realizing it, are encoding the conjugate of that variable. So the time derivative of position is velocity, its conjugate is velocity. You are, without realizing it, or maybe you do realize it, but without thinking about it, you're encoding the derivative of that thing in intervals between pairs of spikes fired by different neurons. So there is a whole sort of parallel coding space, conjugate coding space, that exists alongside population vectors that is encoding the second dimension of a phase space, the time derivative, the conjugate of any other variable that we encode. And in all areas of neuroscience, sensory neuroscience, hippocampal coding of locations, studies of prediction error and value signals in decision-making, conjugate variables come up all the time, okay? A prediction error is the time derivative of a value signal. A velocity is a time derivative of a position signal. So we look at neurons and we see that there are neurons whose firing rates are tuned for velocity and neurons whose firing rates are tuned for position. And we tend to think of those as sort of two different populations of neurons that encode two different things. But in fact, neurons that encode position also encode velocity in this shadow or this conjugate coding domain. Neurons that encode velocity can also encode position. That's a little bit trickier, but that's one of the things that we show in the paper. Velocity-tuned neurons actually encode position in their between cell spike intervals, can do that. And so this whole idea that the brain states that matter, the brain states that encode information are population vectors, it's a little bit like saying that only the time domain matters and not the frequency domain. It's a little bit like saying, we're just going to get by in life never thinking about the frequency domain. You could do that, but it wouldn't be a good idea. And I don't think the brain does that either. And maybe as a sort of a empirical argument for the possibility that that's true, artificial neural network models are also very much built on this population vector coding idea. We take weighted vector sums of firing rates to calculate the activation of each node in, say, an artificial neural network. So in many ways, artificial neural networks are built to decode population vectors. And you don't need a big neuron with a bunch of dendrites to do that. All you really need is a golf ball that, you know, integrates the sums of its inputs. Why would neurons look the way they do if all they're doing is what a simple weighted linear summation on an artificial neural network does? And I like to, so part of this argument is that what real neurons are doing is not measuring firing rates and computing weighted sums to generate activity, to calculate their activity levels. They are doing that, but in addition to that, they are measuring the intervals between pairs of spikes that are fired by different neurons that come in. And in so doing, they are designed to analyze both, you know, the time and frequency domain aspect of their incoming neural activity. So I don't know how much of that you know, makes sense without visual aids or anything, but that's an idea that we're very interested in right now. And it's an idea that that it's only now becoming possible to test, because I think as the next generation of calcium indicators for detecting voltage come down the pike, where we'll be able to do voltage measurements on a very large population scale, similar to the way we are now doing calcium measurements like I did in my talk today. When we were able to do that, when we're able to measure very, very large numbers of spike trains at high temporal resolutions from large numbers of neurons, then it will become possible to sort of test this idea and analyze what information is contained not only in the firing rates, not only within the within cell spike intervals, i.e. firing rates of neurons, but what information is contained within the between cell spike intervals, which we kind of started to call co-firing rates of neurons. And I'm kind of excited that those kinds of questions, you know, may become empirically askable in the near future.
So that sounds quite cool. It's interesting because I teach a dominant paradigm stuff in a computational neuroscience course, and I mostly teach it, but I try to tell students that is the dominant paradigm, and there's other ways, and what does a rate mean and so forth. But one of the things that I don't know if you've gotten to this question, one of the things that I bring up is one of the reasons that is so compelling, this idea of activity level codes and so forth, because it can be joined with Hebbian learning and LTP to get associational learning and changes those representations in a way that's consistent with what those representations mean. And the learning and the representational aspect of things kind of go together in a way that can make sense, right? So you have a pattern that's associated with another pattern, and as they get connected, they get more connected and so forth. And that's one of the reasons that some coding scheme, if you have some new coding scheme, then you have to address the question of learning and how you learn with that and change the computation with that new coding scheme. And that's hard, right? So
right. Well, that's a great question. And I do think that, you know, a learning rule that is essentially sort of error derivative based, you know, can be formulated in this other coding domain. That's an interesting math project, and it's maybe beyond my capabilities, but I don't think it's incompatible. What I do think is a little bit of a cause for concern is that this dominant paradigm of Hebbian learning, which is, you know, also the basis for a lot of AI and machine learning, to do that kind of stuff, you don't need neurons that look and act like real neurons do. You need neurons that look and act like artificial neurons do, you know, golf balls that compute weighted linear sums. And, you know, there are a lot of people in the field, like Bartlett Mell comes to mind, who have kind of been making this point for a long time, that, you know, real neurons are built to do a lot more than what artificial neurons do. And I think that is a little bit, you know, points to the fact that there may be more to the story, and it's not incompatible with the Hebbian learning paradigm at all. It just means that, you know, that there may be a bit more to that story. Again, that we may be kind of focusing on the time domain and ignoring the frequency domain aspect of things, if that makes sense.
So I wanted to ask you, because of your you've done so much work about temporal coding, indeed. Now working with miniscopes. So, at the moment, what the great thing is that they give you signal from so many cells that you can track, but what they give you is some kind of proxy of firing rate. So it seems like to me that after years of building this awareness of the importance of temporal coding and everything now, because when you have a hammer, you go around looking for nails. Now the miniscope might shift back the attention to the idea of firing rate and exactly what you were talking about. But actually now you're thinking about the future could be the voltage, and they could have the temporal resolution to study temporal coding. I'm sure Buzagi will be very happy to hear that. And but yeah, so that was like one question I had, methodological. But the other is like, I think, what's very interesting, or what you were saying, is that perhaps it's one of those rare occasions in which we see at least speculative purpose to this temporal coding in hippocampus, because like, you think about phase precession of place cells, right? A lot of us feel, okay, it's a phenomenon that is so mystifying, and in some way it's telling you something really important about the system. You just don't know what it is. And of course there are theories, and a lot of theories, but you always wonder, is it epiphenomenal, or is it purposeful, or if that even means something, asking that question, but it's telling you something. Now you're saying, with this conjugate interpretation of the time interval between pairs of spikes, whether they come from the single cell or multiple cells, the ability of encoding derivative and state at the same time, it could be applied to many systems, and it could give us a theoretical framework for interpreting why you have that. I mean, there have been other ideas, of course, the plasticity, going back to building sequences, and but yeah, I thought it was interesting.
Well, let me say something about phase perception, actually, because that's something that we addressed in the paper, this hippocampus paper that I recently published with Ryan Gergrich, my graduate student. And so, it has been shown, and it's it's convincing. I think we all accept that there's information encoded not only in the firing rates of place cells, but also in their firing phases. In other words, and phase coding really is, this conjugate coding channel. I mean, ultimately what a phase code is it's, the timing relationship between two different cells. So it is that coding channel. But so a question comes up, a question you could ask is, okay, I accept that spatial information is encoded in firing rates, and I also accept that spatial information is encoded in the phases of, say, place cells. And I accept that if I decode firing rates and phases, I'm going to get more juice out of the lemon. I'm going to get more information about position than if I only encode one or the other, because they both are conveying some information. But now let's ask the following question. Does the information in the phase coding channel come at the expense of information that could otherwise have been encoded in the firing rate channel? Now, I don't know if that makes sense, that question, but what I mean is, these two different coding channels I'm talking about, are they independent with their own capacity? Or if I encode spatial information in phases, am I doing so at the expense of information that I could have encoded about position in firing rates? And in this paper, what we hypothesize, and the title of the paper is An Uncertainty Principle for Neural Coding. And that's a little bit pretentious, but here's the reason why it's titled that, because the hypothesis is this. The hypothesis is that if you decide, I want to encode information about position in the between cell spike intervals, that is the phases, then you must give up capacity for encoding position information in the within cell spike intervals, firing rates. The two coding channels are conjugate and therefore not independent of one another in the sense that, and this is where the uncertainty principle comes in, the more I know about position from looking at phases, the less I can know about position from looking at firing rates. However, and this is a postulate that's in the paper not proven. However, because firing rates and phases, or let's say within cell intervals and between cell intervals, have this special conjugate relationship with one another, they also have a special ability to not interfere with each other when one is assigned to encode information about a variable like position, and the other is assigned to encode information about that variable's conjugate, like velocity. So even though, yes, if I encode position in spike phases, I must give up some of my ability to encode information about position in firing rates. If I encode position information in spike phases, I do not give up information about, I do not give up any capacity to encode information about velocity in firing rates. Why? Because velocity and position bear exactly the same relationship to one another, conjugacy, that firing rates and phases do. And for that reason, you can pack an entire phase space, which has a position and a velocity dimension, into these two coding channels more efficiently. So there is a trade-off for encoding any single variable. If you try to encode position, let's say in firing rates, the more accurately you encode position and firing rates, the less accurately you can encode it in phase. But it is not true that the more accurately you encode position and firing rates, the less accurately you can encode velocity in phase. Velocity is, has a special status, and actually it's very natural to encode velocity in phases when you're encoding position and firing rates. And it's very natural to encode velocity and firing rates when you're encoding position in phases. So,
so you're saying that they are basically representationally independent, but they do compete for information capacity.
There is a true analog of the uncertainty principle at work here between these two coding channels, which is that the more information about one thing you try to pack into one channel, the less information you can pack about that same thing into the other channel. However, the more information you pack about one thing into one channel, the more easy it is to pack information about that one thing's derivative into the other channel. And so, that's why I think like when we talk about, speed cells versus grid cells in the entorhinal cortex, and this is one of the points we made in the paper, we say, oh, speed cells encode speed and grid cells encode position. But what we really mean when we say that is that speed cells encode position, speed in their firing rates, and grid cells encode position in their, speed cells encode speed in their firing rates, and grid cells encode position in their firing rates. But grid cells actually encode velocity in their phases, and speed cells actually encode position in their phases. So it's not really correct to say that speed cells encode speed and grid cells encode velocity. That's only true if you focus on one of the two coding channels. And if you focus on the other, you actually reverse what you see. You see speed cells encoding position, you see grid cells encoding velocity because they're conjugates of one another, if that makes sense. And again, I appreciate that you recognize the dilemma that I faced when I started doing calcium imaging, because it was a dilemma. There was a part of me that didn't want to go there because, I'm so interested in these questions about time coding, and I knew I was going to have to throw all that away. But at the same time, it is a step on the road towards, I think, as these imaging techniques start to tackle voltage, which they're already starting to do, I think on the other side of it, there will be a new ability to answer some of these other questions as well. And the questions about population vector coding are still all very interesting. It's not like they're worthless.
Yeah, no, I mean, I agree. It's not, and I mean, for phase precision, going back to the first question you had, the fact that there is more information about space and phase, looking at the phase, I don't know I don't know how well we understand that in two-dimensional environment. I know you've done some work and other people have done work, but this idea that you can encode position even better with, if you look at defining rate and phase, I don't know how well it's going to play out when you really look at it at 2D. There are studies, but I don't know that we really got to the bottom of that. That's actually.
Well, you're right. It gets very hard to do. And I think that one of the limitations on being able to do that up to now has precisely been the fact that in order to see the information in phase that encodes, say, two-dimensional velocity, let's say, because I do believe that a population of grid cells encodes two-dimensional velocity in their spike phases, relative to one another. I do believe that. But in order to show that would require spike train samples, a couple of orders of magnitude bigger than what you can do with tetrodes or even, silicon probes. You're going to have to get to where you can do, the imaging, the voltage imaging of several thousand grid cells simultaneously before you can actually prove that. You just don't have the N to look at it. And I think that's more than anything been the reason why that's been so difficult. I think if we had a big data set, that would become a lot more tractable.
But speaking of what you can study with this miniscope and the topic of your talk today, I was really curious about something more at the conceptual level. So, you study aversive experience encoded by place cells, and place cells, people have studied the encoding of rewards, so positive experience in place cells. And it really goes back, I guess there are two ways of studying those things with place cells in terms of conceptual framework. One is to what extent those things drive the learning that underlies the representation, or to what extent those things are additional information that gets encoded in the cognitive map.
You're talking about the behavioral learning that occurs during aversive conditioning or avoidance learning.
Yeah. I mean, it really goes back to the original idea of cognitive map, say by Tolman, right? The idea, counter argument to the idea that all learning is stimulus association based on reward. And this idea, he called that, he was really against the Skinner's behavior school. Just call it, in his paper about cognitive maps, he called it the telephone switchboard school interpretation of the nervous system. And this idea that you have to have a cognitive representation that not everything is learned by reward. And then that transfers to, place cells and the cognitive map as intended by O'Keefe and Nadell, and this idea that you have this spatial framework that is learned no matter what, that is incidental learning, latent learning, and it creates this map on which then you can encode, you can use this spatial framework to interrelate the items and events of the experience. And so the idea that an aversive experience is something that you encode on top of this cognitive map. But a lot of more recent work seems to try to explain, attempts to explain place cells in terms of reward-based learning and predictive learning. There have been like on a flurry of studies now. I don't know, maybe they're right, and the origin of the idea was wrong, or maybe they ignored the origin of the idea, or.
Well, I think there's not necessarily a disconnect there. So the way that I feel like I currently think about it, and I think it's not necessarily coming from me, but it's more because I'm following the way the field is going with it, is to sort of really frame it in the paradigm of value-based decision-making and model-based decision-making. as opposed to model-free decision-making. You know, there's this sort of distinction between habit and goal-directed behavior, and hippocampus seems to be much more involved in the goal-directed behavior or model-based decision-making. And you know, the basic tenets of that paradigm are that we when confronted with a choice to behave in one way or another, what we do is when we're using a model-based decision process or a goal-based goal-directed decision process, what we do is we try to predict what world line each of those two behavior choices will take us down, and then try to estimate the goodness of those two, of the outcomes that will result. So there's two steps to that. One, what will be the outcome of choice A versus choice B? And two, what is the goodness of the outcome that will result from A versus from B? And our ability to predict what outcome will result from our choice is only as good as our model of the world. And so we have to have a good model of the world in place to do that. And that's in some sense what, you know, a cognitive map is good for that, right? Because, you know, it's good to know that if I take 3 rights is the same thing as a left, you know. That should be built into my world model so I can make good predictions about what outcome will follow from choice A from choice B. And there doesn't have to be any, you know, reward going on for me to be building a better model of the world all the time, you know, learning what happened, you know, how causal relationships exist in the world. So, you know, this kind of latent learning of the structure of the world, you know, is perfectly compatible with the idea that someday I'm going to need this model to make a prediction that's going to drive my choice, you know. So there's not I don't think there's an incompatibility there. The idea that latent learning occurs, you know, in advance of when what's being learned is needed. So does that sort of make sense? But I do think that, like, when an aversive stimulus comes along, it does sort of changes the demands upon that representation that you're using. And it may be necessary to sort of restructure your model of the world to emphasize or de-emphasize certain predictions, certain choices, you know, in other words, step 1, which is my ability to predict the outcome, and step 2, my attachment of value to one outcome versus another, are not totally independent of one another. When I experience a trauma, an aversive stimulus, I may want to restructure my underlying model of the world to sort of support loss avoidance and minimize risk to my life and limb, because, you know, making a mistake about getting hurt or injured is, you know, so costly that it may be necessary to build your world model around the need to be safe, I guess, is one way of thinking about it. So I don't know if that makes sense to your question, in response to your question, but I think.
No, it does. It does. I mean, I was putting the two things as opposite just so that I could, hopefully, I don't know how clear I was, but trying to explain the thing, you know. In one case, you have this, in one case, you would have the reward driving this placeholder representation. Some people are now thinking about in those terms, you know, you make placeholder map through reinforcement learning, but the original idea was now you don't need reward to set this up, and then you use this framework to add information of, you know, experience of.
I mean, another example that I kind of like, the analogy that I like to use in questions like this is that, you know, there's no such, you know, going back to the fundamental principle, a neural code is a system for mapping states of the world onto states of the brain, right? Well, there are infinitely many different ways to map states of the world onto states of the brain. There's no one answer to how do you encode states of the world and states of the brain. You can do it in so many different ways. And so then, you know, that kind of begs the question, okay, well, what makes one code better than another code? You know, if I've got a choice between building this code versus this code, you know, why would I choose one or the other? What makes one better than another? And there's no right answer to that question either, because the answer to the question, what is a good code, depends on what you're going to be using the code for. And an example I like to give for that is like, you know, if I ask you to multiply 1,627,000 times 723 in your head, you're not going to be able to do that, and very easily. But if you punch those numbers into a calculator or onto your computer, it'll come out in less than a millisecond. Because the way that computers encode information about numbers makes it very easy to solve those kinds of problems. And the way our brains encode information about numbers does not make it very easy to solve those kinds of problems, but those are not the kinds of problems we were asked to solve on the savannah, right? So we encode information and so I think that when something important happens, like a shock on a track, like what we were talking about earlier, the answer to the question, which code is better than the other, changes, because now my behavioral demands have changed. And so I have to change my code because which code is a good code? The things that I want to encode invariantly versus non-invariantly, the things that I want to pattern separate versus pattern complete are now different because of that experience. And I have to rebuild my code and make it better because the answer to what is a good code is no longer the same because of that motivational experience, if that makes sense.
Yeah.
But the way, sorry, go ahead, Francesco.
I don't know, I was just nodding, yeah.
But the way you're looking at these things in terms of these long time scales that look at how animals extinguish and then potentially reinstate, and this recent collaboration of yours with the
Adhikari, yes.
Yeah, Adhikari Lab.
Yeah, and I should give most of the credit. They really did most of that work on their own. We helped them with the mini scope and some data analysis advice, but Peter Schuett, the lead author of that, and Avi yeah, they really did a great job on that. But go ahead.
But in that instance, you have not just like a kind of a reshuffling or the remapping is sort of one idea, but there's actually this like amplification of the resolution of that space long after the aversive episode has vanished. And so, I mean, it leads to some interesting questions about how much generalization can happen across contexts, right? So will that spatial area be amplified? Because we constantly think now of place cells as remapping in the face of everything, you know, instantaneously almost. Yet how stable are these fear-induced maps? And, you know, what are the things that can potentially, you know, where does generalization come from versus context specificity? Because everyone talks about the context specificity with hippocampus.
Yeah. So, and I think there's different words for these things. So like when you say context specificity versus generalization, it's kind of, you know, I think, correct me if I'm wrong, but it's a little bit analogous to saying pattern separation being similar to context specificity, pattern completion being similar to generalization, or invariant coding being similar to generalization. You know, these different terms for the same principle, which is lumping versus splitting, you know, that kind of, you know, thing. And you know, I guess I would go back to what I was just saying to Francesco, you know, when should you lump and when should you split? When should you pattern separate? When should you pattern complete? There's no right answer. It's really about what the task demands or what the decision pressures you face at any given time are. And so when we look at the hippocampus and see remapping, as you say, in response to everything or happening all the time, and this dynamic fluidity going on at all the time in the hippocampus, it's easy to think that the hippocampus is a splitter, you know, that it's more of a splitter than a lumper, you know, that it's just so unstable, you know, and our ability to study the long-term dynamics of representations using techniques like calcium imaging, you know, that Ziv paper from the Schnitzer lab from 2013, that sort of first in vivo calcium imaging paper, you know, it addressed that question, I think, for the very reason that for the first time it became possible to look, you know, over time in ways that weren't possible before, the dynamics of the hippocampal representation. And when we saw what we were able to see for the first time when those papers started coming out, that, oh my God, the hippocampus, the cognitive map is a mess. You know, it changes every day. It's not a stable representation at all. You know, it's easy to panic and think, oh, you know, the hippocampus just remaps in response to everything. But I think that, you know, we need to push the needle back the other direction and recognize that probably and I'm trying to relate this back to your question about context specificity versus generalization. You know, maybe what we're seeing there is that maybe the lesson in that is that generalization is a bit more of a special case than we previously thought. You know, that our ability to invariantly represent things, our ability to pattern complete, our ability to identify stimuli generalized across various conditions may be more the exception than the rule. You know, the world is full of so many, the world itself is a mess. You know, it's not just the hippocampus, the world is a mess. And so why should we be surprised that the hippocampus is a mess? It's just, there's very few things that come into us through our senses that are actually stable enough to grab onto and hold onto. And maybe that's why we don't see as much of it as we might have expected. So yeah, I don't know, that's a bit of a philosophical ramble on it.
Could you help me understand then these experiments in which people train an animal in some situation and then label the neurons that had CFOS activation during that time, and then they activate those neurons again, and it's like, wow, those cells encoded that state of the world and encode it forever. And if you ever activate them again, it's just as if that state of the world happened.
Wait, I think maybe you're thinking about like the memory tagging experiments from Susumu Tanagawa, like in the dentate gyrus and so on.
Yeah.
Yeah, well, so there's something actually very interesting about that, which is that, you know, those experiments were done in the dentate gyrus. And now maybe there's been others more recently, but those original experiments were done in the dentate gyrus. And one of the reasons they chose the dentate gyrus as opposed to other structures for those experiments is because it has a uniquely sparse code for space and for context, meaning that it is a single dentate gyrus cell does seem to, encode a specific location or context in a way that a single, say, CA1 cell or other brain cell might not, because in CA1, which is the area we were looking at today in our experiments, you have a much more distributed code, and the importance of any single neuron's activity is correspondingly diminished, if that makes sense. So
yeah,
maybe if we were
dentate gyrus is not a mess.
Say that again?
The dentate gyrus is not a mess. Is that what you're saying?
It's less, maybe less of a mess. But there is a difference there. I mean, there's a continuum between, you know, sparse and distributed coding, and where you really see the mess and the remapping, I think, is that's kind of a feature of these areas that have very distributed coding schemes, and maybe less so of something like the dentate where you see much more sparse coding. That's a good point, you know, to raise actually.
I mean, we should also say, okay, it's true. We observe now all these drifting of the representation in the hippocampus. It's being seen even better now with these miniscopes and calcium. It turns out that there were hints to that in the literature for a very long time. But there's also a remarkable stability. I mean, you can get sometimes place cells or, you know, fighting in the same spot, the same environment for a long time after many days, and they still fire in the same spot. Grid cells, I mean, in my experience and all other studies, they pick a reference frame in one environment and they stay with it, you know, for weeks. And, you know, every time the phase of the grid, well, you know, it's hard to track the same cell for many, many days. You're not sure with tetrads, but for example, the orientation of the pattern stays the same in the same grid module, and you go on for weeks. And, you know, in one manipulation, the grid has these axes with respect to the external world, in another has another one, and it stays like that for weeks, you know. And so there is also a remarkable, you know, degree of stability in these systems. It's not all drift. It's not all a mess. Let's just put it that way. Let's just reassure Charlie that it's not all a mess.
And no, that's true. It's not. And I think, you know, and again, it's kind of like what you said earlier about everything, you know, if you have a hammer, everything looks like a nail. Well, you know, back when John O'Keefe first discovered place cells and found, you know, these neurons that are very stable, it's easy to sort of focus on those cells and kind of just assume that the other ones aren't place cells or whatever. But now that we have this ability to look at populations, you know, larger populations over longer periods of time, you know, we see that our simple interpretation of what place cells do was a little bit lacking. We overestimated their stability, but as you say, you know, let's not go too far in the other direction. You know, they are still stable. It's just they're not as stable as we kind of assumed when they were first discovered, and that was all we could see, you know. But yes, you're absolutely right.
Mm-hmm.
Excellent. I think we're running out of time. I get the feeling we could riff for a while on this stuff. But thank you for joining us. And this has been Neuroscientists Talk Shop. Thank you, Tad Blair. Thank you, Francesco and Todd and Charlie. And we'll see you guys soon.
Thank you for doing this. This is a wonderful format. It's very intellectually stimulating, and I applaud you for having this forum. It's really wonderful.
Thank you all. This is lots of fun, and we're happy that we get to do it and that people play along.